A dead star's magnetic field can literally bend the fabric of reality. These cosmic corpses are called magnetars, and they are among the most extreme objects in our universe. By the end of this journey, you will understand how these stellar ghosts challenge the very laws of physics. We will uncover how a star's violent death can forge a magnet so powerful it cracks the star's own surface and twists the space around it. What forgotten force could turn a dead star into a cosmic powerhouse? The story begins not in a quiet graveyard, but in a cosmic forge of unimaginable power. To understand the dead star with a magnetic field strong enough to warp spacetime, we first need to witness the spectacular and violent event that creates it. Think of a star not like our stable sun, but a true giant, born with a mass many times greater. These stellar titans live fast, burning through their nuclear fuel in a blaze of cosmic glory over just a few million years. Their entire existence is a constant battle, a fragile balance between the outward push of energy from fusion at their core and the relentless inward crush of their own immense gravity. This balance cannot last forever. When the fuel finally runs out, that battle ends in an instant. Gravity wins. The star's core, no longer supported by outward pressure, catastrophically collapses in upon itself. The outer layers plummet inward at a significant fraction of the speed of light, only to rebound off the now unimaginably dense core in one of the universe's most energetic events, a supernova explosion. For a brief moment, this single dying star can outshine an entire galaxy. What it leaves behind is the stellar graveyard, and the nature of the corpse depends entirely on the mass of that original star. For our story, the remnant is a neutron star. Imagine taking a mass greater than our entire sun and crushing it down into a sphere no wider than a city. A single sugar cube-sized piece of this material would weigh as much as a mountain. The physics here is extreme. Protons and electrons are forced together under such incredible pressure that they merge into neutrons, creating a sea of the densest, strangest matter in the observable universe. This is the baseline, the standard resident of this particular cosmic cemetery. But for a rare few, about 1 in 10 of these neutron stars, the collapse is even more special. During those final milliseconds of the star's life, as the core implodes, a perfect storm occurs. The star's original magnetic field, which was already substantial, gets caught in this violent contraction. Like a skater pulling in their arms to spin faster, the collapsing star concentrates and amplifies that magnetic field to levels that defy easy comprehension. This is the birth of the Magnetar. It is not a random fluke, but a specific, predicted outcome when the conditions during a supernova are just right. This violent origin story explains why these objects are not just dense, but are imbued with a force so potent it becomes the defining feature of their afterlife, shaping everything that happens next. That baseline density is just the beginning. To truly grasp a magnetar, you must first understand the sheer scale of the force it wields. Think of a typical neutron star, already a cosmic powerhouse. Its magnetic field is 1 trillion times stronger than the one that gently guides our compasses here on Earth. That number is almost impossible to visualize. But a magnetar takes that already unimaginable power and multiplies it by another 1,000. It is not just a stronger version of the same thing, it is an entirely different class of object, defined by this one overwhelming attribute. To put a scale that vast into a human context, imagine if a single magnetar were placed halfway between the Earth and the Moon. Its magnetic field would be so overwhelmingly powerful that it would erase the magnetic data from every single credit card, hard drive, and electronic device on our entire planet. That is the level of influence we are talking about, a force that can reach across hundreds of thousands of kilometers of empty space and fundamentally alter the world we live in. This is not a gentle pull, it is a cosmic sledgehammer. On the surface of the magnetar itself, this force becomes truly tangible. The magnetic field is so intense that it exerts a physical stress on the star's own crust, a solid shell of iron nuclei packed into a crystalline lattice tougher than diamond. This stress builds and builds until, like tectonic plates on Earth, the crust suddenly cracks. These are Starquakes, seismic events on a neutron star that release more energy in a fraction of a second than our Sun will emit in 100,000 years. But the influence goes even deeper than the surface. The field is so strong it can affect the very fabric of empty space around the star, a concept predicted by Einstein's theory of general relativity. It can twist the quantum vacuum, influencing how light itself behaves and creating conditions where the rules of physics as we know them are pushed to their absolute limit. This moves the idea from an abstract cosmic curiosity into a concrete, almost unbelievable physical reality. This perfect storm of creation requires a very specific cosmic recipe. It starts not with just any dying star, but with a particular kind of stellar giant. This progenitor must be massive, yes, but it also needs to be spinning rapidly, carrying a significant amount of rotational energy from its birth. When this star finally exhausts its fuel and its core collapses, the laws of physics take over in a spectacular way. The principle of conservation of angular momentum comes into play, the same rule that causes a spinning ice skater to whirl faster when they pull their arms in. As the star's core implodes from a size larger than Earth down to a city, its rotation accelerates dramatically, spinning up to complete a full revolution in mere milliseconds. At the same time, the star's original magnetic field, which was already woven through its structure, gets caught in this violent contraction. The field lines are squeezed, wound up, and amplified to an almost incomprehensible degree. But the real engine is what happens inside the newborn neutron star. For a brief, chaotic moment, the interior is a seething, super-hot fluid of neutrons and other exotic particles, churning with tremendous energy. This rapid spin combined with that turbulent motion acts like a cosmic dynamo, a natural generator on a stellar scale. It converts the immense rotational and thermal energy into magnetic energy, boosting the field's strength by a factor of 1,000 or more in the blink of an eye. This is the critical, fleeting window that creates a magnetar. If the original star was spinning just a bit too slowly, or if the collapse played out slightly differently, that dynamo effect never reaches its full potential. The result would be an ordinary neutron star, still an extreme object, but lacking that universe-bending magnetic signature. And if the star was even more massive, the entire core would collapse past the point of no return, forming a black hole instead. This precise and volatile recipe explains why magnetars are so exceptionally rare in our galaxy, perhaps only a few dozen among the hundreds of millions of stellar corpses. Each one we detect is a precious relic of a uniquely violent and perfect moment in cosmic history, a snapshot of physics pushed to an absolute extreme. That unimaginable magnetic force has a very tangible and violent effect on the star itself. The crust of a magnetar is not a passive shell, it is a battlefield. Picture a solid surface forged from iron nuclei, locked into a crystalline structure denser than any material we could ever create. Yet this incredible shell is constantly being stressed and pulled by the magnetic field threading through it. The strain builds over years, decades, perhaps centuries, until the crust can no longer hold. It fractures. This event is a starquake, and it is one of the most powerful releases of energy in the known universe. In the blink of an eye, as the crust shifts and cracks, it unleashes more power than our Sun will radiate over 150,000 years. The sheer scale of that energy is difficult to process. It is a cataclysm contained on an object the size of a city, and it sends a shudder through the very fabric of space around it. This fracture does more than just shake the star. It acts like opening a valve on a pressurized system. A flood of pent-up magnetic energy is suddenly released, accelerating particles to near light speed. The result is a brilliant, deadly flash of X-rays and gamma rays that screams across the galaxy. For us, watching from a safe distance of thousands of light years, that flash is a beacon. It is our primary signal that a magnetar is not just a dormant corpse, but an active, seething entity. By studying the light from these bursts, astrophysicists can perform a kind of cosmic seismology. Just as geologists learn about Earth's inner layers by measuring how seismic waves travel through our planet, scientists can analyze the patterns in a magnetar's X-ray afterglow. The way the star rings and vibrates after a quake tells a story. It reveals clues about the thickness and strength of that impossible crust, the density of the fluid interior, and the precise configuration of the magnetic field locked within. Each starquake is a violent message, a data point sent from an extreme frontier of physics, helping us map the interior of a world we can never hope to visit. These starquakes are merely the prelude to the magnetar's true fury. Occasionally, a magnetar does not just crack, it erupts. The most dramatic displays are known as giant flares, where a catastrophic and sudden reorganization of the magnetic field near the star's surface unleashes an explosion of almost mythical proportions. For one blinding instant, this single dead star can outshine our entire Milky Way galaxy in gamma rays, even from tens of thousands of light years across the void. The energy released is staggering, equivalent to what our sun would radiate over hundreds of thousands of years, but compressed into a mere tenth of a second. This is not a simple flash. It is the magnetic field itself snapping into a new, lower energy configuration, a process that violently accelerates particles and creates a fireball of radiation so intense it briefly outshines every other source in its frequency across the cosmos. These specific outbursts have led scientists to classify the sources as soft gamma repeaters, a name that sounds almost gentle but describes objects of immense sporadic violence. They are named for their repeated, unpredictable bursts of slightly lower energy gamma radiation, the constant rumbling that occasionally builds into a world-shattering roar. The power of these events is not theoretical. In December 2004, a magnetar named SGR 180620, located roughly 50,000 light-years away in a different spiral arm of our galaxy, unleashed a giant flare. In that moment, for a fifth of a second, it became the brightest object ever detected outside our solar system in any wavelength. The pulse of radiation was so powerful that it actually reached Earth and measurably ionized atoms in our planet's upper atmosphere, a tangible effect from an explosion halfway across the galaxy. This was a humbling reminder that the universe is not a passive backdrop, but an active, sometimes violent participant. These flares are far more than just cosmic light shows. They serve as direct, unforgiving probes into magnetic field physics operating at its absolute limit. By studying the light curve, the spectrum, and the afterglow of these eruptions, astrophysicists can witness energy transfer mechanisms that dwarf anything possible in our solar neighborhood. They reveal how magnetic energy can be stored, twisted, and then catastrophically released in a process that literally lights up the galaxy, offering us a front-row seat to forces that shape the most extreme environments in existence. This staggering power brings us to the very heart of the mystery. A magnetar's magnetic field does more than just crack its own surface and light up the galaxy. It actively reshapes the stage on which it sits. The key to understanding this lies in one of the most profound insights in all of physics, Einstein's theory of general relativity. The theory tells us that what we perceive as gravity is not a force pulling objects together, but rather the curvature of spacetime itself. And crucially, it is not just mass that causes this curvature, but any form of energy. Mass is simply one highly concentrated form of it. Light carries energy. And a magnetic field, especially one of incomprehensible strength, contains a truly stupendous amount of energy. The energy density packed into the space around a magnetar is so phenomenally high that it ceases to be just a magnetic phenomenon. It becomes a gravitational one. The field itself adds to the star's gravitational pull and actively contributes to the bending of spacetime around the stellar corpse. Think of it this way. Around an ordinary star or planet, spacetime is curved primarily by the mass at the center, like a heavy ball resting on a stretched rubber sheet. But around a magnetar, the intense magnetic field surrounding that central mass is like a thick, viscous syrup filling the depression, adding its own weight and deepening the curve. The field and gravity are no longer separate actors, they are intertwined, two expressions of the same underlying distortion of reality. This leads to predictions that sound like pure science fiction. A rapidly spinning magnetar, with its unimaginably powerful field co-rotating with it, should literally drag the fabric of spacetime around as it spins. This effect, known as frame dragging, is like twisting honey with a spoon. The spacetime itself gets caught in the rotation. While this effect is tiny around planets, for a magnetar it could be significant enough, in theory, to one day be measured. This makes magnetars more than just cosmic curiosities. They are natural laboratories for physics at its most extreme. They offer us a unique testing ground, a place where the two great pillars of modern physics, Einstein's gravity and quantum electromagnetism, meet and interact in ways we can barely model on Earth. Studying them is an attempt to listen to the universe itself as it strains against the very rules we have written, offering whispers of how all fundamental forces might one day be woven into a single, coherent tapestry. The magnetic field's influence goes even deeper than bending space. It begins to rewrite the rules of matter itself. To understand the environment around a magnetar, we must shift our perspective from cosmic scales down to the quantum realm. The field strength here is so unimaginably high that it crosses a threshold into a domain of physics called quantum electrodynamics. In this regime, the very idea of empty space breaks down. According to quantum theory, the vacuum is not truly empty, but a seething, bubbling sea of virtual particles, fleeting pairs of matter and antimatter that constantly pop in and out of existence. Under normal conditions, these particles vanish almost instantly, but near a magnetar, the magnetic field is so powerful it can grab hold of these virtual pairs, lending them real energy and pulling them apart before they can annihilate. The vacuum itself becomes an active, polarized medium. One of the strangest consequences is a phenomenon called vacuum birefringence. Imagine a clear crystal of calcite. When you shine a light through it, the beam splits into two, each with a different polarization. In the magnetized vacuum around a dead star, empty space itself acts like that crystal. Light traveling through it does not move in a straight line as we expect. It splits and its properties change based on its polarization relative to the field. This is not a minor optical trick. It is the fabric of reality behaving like a tangible substance under extreme magnetic stress. The effects on actual atoms are even more dramatic. In a field 1 trillion times stronger than Earth's, an atom cannot maintain its familiar spherical shape. The negatively charged electrons are pinned into incredibly tight, fast orbits perpendicular to the magnetic field lines, while their motion along the field is less restricted. The result is that the entire atom gets stretched into an elongated, needle-like cylinder, completely distorted from its natural form. This means the very building blocks of ordinary matter are fundamentally altered in this environment. For astrophysicists, these are not just abstract theoretical predictions. They are potential keys to observation. If vacuum birefringence is occurring, it should leave a specific, detectable signature in the X-rays and gamma rays streaming from a magnetar's surface. The polarization of that light would carry the imprint of its journey through the twisted quantum vacuum. By analyzing that light with future space telescopes, we could have direct observational proof of quantum electrodynamics operating in a regime forever beyond Earth-bound laboratories. The Magnetar's magnetosphere thus becomes the universe's most powerful natural experiment, a place where the quantum world is magnified to a cosmic scale and written in radiation for us to decode. This precise cosmic clockwork offers us a direct line into the Magnetar's hidden heart. While their violent outbursts grab headlines, it is the steady, rhythmic ticking of many magnetars that provides their most revealing data. A significant number of these magnetic monsters also function as pulsars. As they spin, beams of intense radiation, channeled by those unimaginable magnetic fields, shoot out from their magnetic poles. If Earth lies in the path of one of these sweeping beams, we see a regular pulse of light, a flash with every rotation, like the beacon of a lighthouse on a truly cosmic scale. The regularity of this pulse is astonishing, often precise to within a fraction of a millisecond over years, but for magnetars, this clock is far from perfect. Their rotation tells a story of constant struggle. The primary force acting on them is magnetic braking. That immense field acts like a giant brake in the vacuum of space, sapping the star's rotational energy and causing it to spin down gradually over centuries. Scientists can measure this slow deceleration with incredible accuracy by tracking the timing of the pulses. It is from this spin-down rate that we can actually calculate the strength of the magnetic field, turning the star's own rotation into a remote diagnostic tool. Yet this slowdown is not always smooth. Magnetars experience sudden, unpredictable jumps in their rotation speed called glitches. Imagine a spinning figure skater who, without warning, suddenly pulls their arms in tighter and spins faster for no apparent reason. These events are thought to be caused by sudden shifts inside the star, perhaps where the superfluid core uncouples from the solid crust, transferring momentum in a sudden burst. Even more telling are the tiny wobbles in the pulse timing that follow a starquake. The catastrophic cracking of the crust changes the star's shape ever so slightly, which alters its moment of inertia and causes a minuscule shift in its rotation. By monitoring these minute changes in the pulse arrival times, astrophysicists can perform that cosmic seismology, deducing the size and nature of the quake that caused it from thousands of light years away. This jittery, imperfect clockwork is actually a gift. It makes the magnetar's internal dynamics visible. On a perfectly stable star, these subtle internal rearrangements would be hidden from view. But here, every glitch, every tremor-induced wobble, is written plainly in the timing of the flashes we receive. It is a direct transmission from the interior of an object we can never visit, a narrative of stress, fracture, and adjustment told in the precise language of milliseconds, revealing the ongoing life of a stellar corpse. The clockwork of a distant star offers a direct test for these extreme theories. In the constellation Cassiopeia, roughly 10,000 light-years from Earth, lies one of the most instructive magnetars ever observed. Catalogued as 1E2259+586, it belongs to a special subclass known as an anomalous X-ray pulsar. The name itself is a clue to its mystery. This object pulses with X-rays, but its steady glow is hundreds of times brighter than its slow spin down should allow. Where is all that extra energy coming from? The leading hypothesis points directly to the heart of the magnetic field itself. Scientists believe the field is not perfectly frozen into the star, but is very slowly decaying, dissipating its unimaginable energy over millennia. This decay acts like a built-in furnace, continuously heating the star's interior and its solid crust, which then radiates away that heat as the powerful, steady X-ray glow we detect. It is a cosmic battery running on magnetic decay, and its output provides a rare window into the long-term fate of these fields. This star's story became even richer in June 2002. After years of quiet, steady emission, 1E2259 plus 586 erupted. It produced a spectacular outburst, firing off hundreds of individual X-ray bursts over several hours and increasing its persistent X-ray brightness 80-fold in an instant. This event was a textbook example of a Magnetar starquake and its aftermath. The sudden cracking of the crust released a flood of trapped magnetic energy, which then lit up the surrounding magnetosphere. For astronomers, it was a perfect storm of data. They could watch the star's rotation suddenly change, observe the burst activity, and then track the long, slow cooling of the star's surface as the extra heat from the outburst gradually radiated away into space over the following months. Studying this single object and others like it allows researchers to perform critical forensic work. By measuring how the star cools after an outburst, they can estimate the thickness and composition of its crust. By analyzing the pattern of its steady X-ray glow, they can test different models of how the magnetic field decays within the star's superfluid core. Each data point helps piece together the life cycle of magnetic energy in these corpses, from its violent birth in a supernova through its active, quake-ridden middle age to its eventual slow fade over hundreds of thousands of years. 1E2259 plus 586 is not just a distant curiosity, it is a natural laboratory, its light carrying encoded details about physics in a realm we can never recreate, telling the ongoing story of a magnetic field so strong it outlives the star that created it. But this magnetic dominion could extend far beyond the star itself, raising a profound cosmic question. Could a Magnetar actually possess a planetary system? The idea seems like a contradiction, a place of serene orbits built around a heart of pure chaos. Yet theoretically, it is possible. Planets might form from the rich debris field left behind by the original supernova explosion, a second-generation family born from the ashes of their progenitor star. Alternatively, a wandering planet could be captured by the Magnetar's immense gravity later in its life, pulled into a doomed dance, but to call such a world hostile would be a breathtaking understatement. Any planet in orbit would be immersed in a perpetual storm of radiation. The surface would be scoured by intense X-rays and gamma rays, making the concept of a biosphere, as we understand it, simply impossible. The radiation would not just sterilize the surface, it would likely strip away any substantial atmosphere over time, leaving behind a barren, irradiated rock. Yet, if that world somehow retained a magnetic field of its own, the interactions would become a spectacle of pure physics. The planet's magnetosphere would be no protective bubble, but a point of violent contact. As it plowed through the Magnetar's impossibly strong field lines, it would generate electrical currents of planetary scale, potentially heating the interior through a process called electromagnetic induction, like a kettle heated not by fire but by magnetic friction. The most visible sign would be auroras, but not like our gentle northern lights. These would be global, permanent, and unimaginably bright, likely shining across the entire electromagnetic spectrum as charged particles flooded the planet's magnetic poles. For an observer, this dying world would be lit by continuous, silent storms of light, a beautiful and lethal side effect of its proximity to power. For astrophysicists, such a system, while devoid of life, would be a laboratory beyond compare. The planet's orbit would modulate the Magnetar's emissions. As it passed through different parts of the magnetosphere, it might trigger periodic bursts or cause detectable dips in the star's X-ray output, a telltale heartbeat revealing its presence. Studying this interaction would provide a direct, real-time look at how planetary and stellar magnetospheres couple under the most extreme conditions imaginable, teaching us about the fundamental physics of plasmas and magnetic fields in a way no simulation ever could. It would be a testament to the universe's ability to create relationships of pure force, where connection is measured not in biology, but in raw, luminous energy. The search for the source of fast radio bursts has consumed astronomers for nearly 2 decades. These brilliant flashes, lasting just milliseconds, pack more energy than our Sun emits in 80 years, and they arrive from galaxies millions or even billions of light years away. For years, their origin was a complete enigma, a cosmic signal with no clear sender. Then, in April 2020, a breakthrough came not from the distant cosmos, but from our own galactic backyard. A known magnetar named SGR 1935+2154, located about 30,000 light-years away, entered an active phase. As telescopes watched, it did something unprecedented. It emitted a powerful, millisecond-long burst of radio waves. While this burst was thousands of times less energetic than the typical extragalactic fast radio burst, its profile was a perfect match. The duration, the structure, the way the signal dispersed, it all aligned. For the first time, we had caught a magnetar in the act of producing a fast radio burst-like event. This was the smoking gun, a direct link between these mysterious cosmic signals and the most magnetic objects in the universe. This single observation transformed the entire field. It strongly suggests that at least a significant fraction of fast radio bursts, particularly the non-repeating ones, could be the signature of cataclysmic magnetar activity in distant galaxies. Imagine a giant flare or an extreme starquake on a magnetar in a galaxy 100 million light-years away. The initial blast of gamma rays and X-rays might be beamed in a direction away from us, invisible to our telescopes. But the shockwave from that event, plowing through the magnetar's own intense magnetic field and the surrounding debris, could generate that brilliant, fleeting flash of radio waves we detect as a fast radio burst. The magnetar, in its most violent moments, becomes a cosmic lighthouse, its radio beacon sweeping across the universe to briefly outshine everything else in its frequency. This connection does more than solve a puzzle. It elevates magnetars from stellar oddities to central players in high-energy astrophysics. They become potential engines for some of the most powerful and mysterious transient events we can observe, acting as a crucial bridge between the physics of dead stars and the large-scale structure of the cosmos itself. By studying the bursts from our local magnetar, we now have a template, a key to begin decoding the signals from the far reaches of space, listening for the echoes of stellar corpses in the deep. The true nature of a magnetar is locked away beneath its iron crust. To grasp the source of its power, we must take a conceptual journey into the heart of the star itself, into a realm where matter itself surrenders to new rules. The crust, that city-spanning shell of crystalline iron, is merely a thin, brittle skin. Beneath it lies an ocean, but not of water. This is a sea of neutrons, the crushed remains of atomic nuclei, flowing with almost no friction. This neutron fluid is likely a superfluid, a state of matter that defies our everyday intuition, where it can flow around obstacles without losing energy and create microscopic whirlpools that last forever. Mixed within this neutron sea are protons, and here lies a critical clue. In the intense pressure and cold of a neutron star's interior, these protons are believed to form a superconductor. Now, in a normal superconductor on Earth, magnetic fields are expelled, a phenomenon called the Meissner effect. But a magnetar's field is far too powerful to be expelled. Instead, the magnetic field fights its way into the superconducting region, threading through it not as a smooth field, but as countless discrete filaments of magnetic flux, like a cosmic bundle of spaghetti frozen in the superconducting proton soup. The long-term life of the magnetar, the slow fade of its field over hundreds of thousands of years, is governed by the complex and turbulent dance between these magnetic filaments and the superconducting fluid around them. This interaction determines how quickly the star's magnetic energy is converted into heat, which then radiates away as the steady X-ray glow we observe. It is a slow-motion battle that dictates the star's active lifetime. Venture deeper still, and the physics becomes even more speculative and extraordinary. At the very core, pressures may be so immense that neutrons themselves break down. They might dissolve into a soup of their constituent particles, creating a state of matter called quark-gluon plasma, or give rise to exotic particles known as hyperons. These are forms of matter that cannot exist stably anywhere else in the observable universe, not even in the largest particle colliders on Earth. This is where the Magnetar becomes our greatest cosmic probe. We cannot see this interior directly, but the magnetic field acts as a diagnostic tool. The rate at which the field decays, measured by the star's changing spin and its cooling X-ray emissions, depends entirely on the conductivity and composition of these hidden layers. A core of free quarks would allow the field to evolve differently than a core of hyperons or a simple neutron superfluid. By patiently observing a magnetar's behavior over years and decades, astronomers are essentially performing a deep space MRI scan. They are using the slow leak of magnetic energy as a signal to map the structure and physics of a world we can never visit, listening to the whispers of matter under conditions so extreme they rewrite the textbook, revealing secrets from the very edge of what is possible. The physics of a magnetar's heart is a problem that can only be solved in a digital universe. Since we cannot recreate these conditions in any laboratory on Earth, scientists have turned to the next best thing, building them inside the world's most powerful supercomputers. This field is computational astrophysics, and its goal is to simulate the unsimulatable. The challenge begins with the magnetohydrodynamics, a complex term that simply means modeling how the star's magnetic field interacts with its fluid, superconducting interior and its brittle, solid crust. These simulations must track how magnetic field lines, frozen into the star's material, get twisted and wound up by its rapid rotation, building up immense stress over time. They must then capture the moment that stress becomes too great, when the field lines suddenly snap and reconnect in a violent release of energy, a process that can trigger a starquake or a giant flare. To do this, the computer code must bridge an almost impossible gap in scale. It has to account for the star's global magnetic field, which envelops the entire object, while simultaneously resolving the tiny, localized fractures that might appear in its crust, events separated by a factor of billions in size. Running these simulations requires staggering computational power, making them some of the most intensive projects in all of science. They are digital laboratories where physicists can run experiments that are impossible in reality, tweaking variables like the star's initial spin, the thickness of its crust, or the strength of its magnetic field to see what happens. The insights from these virtual magnetars are not just abstract, they are absolutely crucial for interpreting the real data from our telescopes. When we see a burst of X-rays or a shift in a star's rotation, the simulations provide a possible story for what caused it, a physical model of the hidden drama inside the star. They guide our search by predicting the specific signatures, the unique fingerprints in light and timing, that we should look for in future observations. In essence, these lines of code are our best map to a territory we can never physically reach, turning the raw numbers from a cosmic flash into a coherent narrative of force and fracture. The sheer power of a magnetar stands in stark contrast to its profound scarcity. Our galaxy, the Milky Way, is home to hundreds of billions of stars, and the stellar graveyard is correspondingly vast, littered with the remnants of countless generations. Yet within this immense population, confirmed active magnetars number only about 24. We know they exist because their signatures are unmistakable. The brilliant X-ray glows, the sudden, violent bursts, the slow, steady spin down measured in milliseconds. Space observatories like Chandra, XMM-Newton, and swift act as our sentinels, their unblinking eyes constantly scanning the cosmic dark for these rare flashes of magnetic fury. Each new candidate is a major discovery, a piece of a puzzle we are only beginning to assemble. But the 24 we see are likely just the tip of an iceberg. Theoretical models suggest a far larger population lies hidden in the galactic shadows, perhaps tens of millions of magnetars in total. The majority, however, would be dormant, their once unimaginable magnetic fields having faded after a relatively brief period of cosmic activity. This timescale is key. A magnetar's hyper-strong field may only persist for 10,000 years, maybe 50,000, a mere blink in the multi-billion-year life of a galaxy. This explains the stark imbalance. We are catching only the rare, active specimens in their brief, brilliant window of fury, while the quiet, faded majority blend into the background hum of neutron stars. Building a complete galactic census of these objects is not just an accounting exercise, it is fundamental science. By understanding how many are born and how they evolve, we can answer deeper questions. What fraction of massive stars die in the specific, perfect storm that creates a magnetar? How does their intense radiation and particle wind over their active lifetimes influence the surrounding interstellar gas, potentially triggering or suppressing new star formation in their neighborhoods? And by studying the full range from the hyperactive bursters to the silently fading ones, we can finally chart the entire life cycle of magnetic energy in the universe, from its explosive birth to its quiet, ultimate decay. Every new magnetar we find adds a data point to this map, helping us understand not just the corpses themselves, but the magnetic heartbeat of the entire galaxy. This places them among the most powerful natural laboratories in the cosmos. While we watch their brilliant flares and measure their steady pulses, we are doing far more than just cataloging stellar oddities. We are conducting fundamental physics experiments on a galactic scale, probing the laws of nature under stresses that dwarf anything achievable on Earth. The first great test involves gravity itself. Einstein's theory of general relativity makes precise predictions about how massive, spinning objects should warp the spacetime around them. A magnetar, with its immense density and rapid spin, is a perfect candidate to reveal these subtle effects. If one were found in a binary system with a companion star or planet, the orbit of that companion would not be a simple ellipse. The intense gravity of the magnetar would cause the entire orbit to slowly rotate or precess, like a spirograph drawing in the sky. Measuring that precession from thousands of light years away would provide one of the cleanest tests of general relativity in the strong field regime, far beyond what our solar system can offer. Then there is the matter itself. The core of a neutron star represents matter pressed to its absolute limit, a state governed by the strong nuclear force. A precise relationship between this unimaginable density and the resulting pressure is called the equation of state, and it is one of the great unsolved puzzles in nuclear physics. Different theoretical models predict different maximum masses and sizes for neutron stars. A magnetar, by virtue of its intense magnetic field, can sometimes reveal its size more clearly through phenomena like starquakes and cooling rates. Each observation helps us rule out certain equations of state, telling us what the fundamental building blocks of matter cannot be, and inching us closer to understanding the true nature of the force that holds atomic nuclei together. As we have seen, the magnetic field itself pushes quantum electrodynamics into uncharted territory. The predicted vacuum birefringence, where empty space acts like a crystal to split light, is a direct challenge to our quantum understanding of nothingness. Detecting the specific polarization signature in a magnetar's X-rays would be a monumental confirmation of quantum field theory in an entirely new realm. Some speculative theories venture even further, suggesting that magnetic fields of this magnitude could become so energetically favorable that they catalyze the decay of protons, a process that would violate a fundamental symmetry in particle physics. While this remains a fascinating and unproven idea, it highlights the sheer extremity of the environment. Every flicker, every glitch, every burst of radiation from a magnetar is data from an experiment we did not build, in a laboratory we cannot visit. By carefully decoding these signals, we are simultaneously testing the theory of the very large general relativity and the theory of the very small quantum mechanics in a single, dense, spinning package. It is a convergence of physics frontiers, all written in the light of a dead star. The next leap in understanding these magnetic monsters will come from our own ingenuity, from a new generation of eyes trained on the cosmos. Our current view, while revolutionary, is still fragmented, like trying to reconstruct a symphony by listening through a keyhole. The future promises to open the door wide. In the coming decade, a suite of advanced observatories, both in space and on the ground, will transform magnetars from distant points of light into intricate, three-dimensional maps of magnetic force. The European Space Agency's Athena mission, a flagship X-ray observatory slated for launch in the 2030s, represents a quantum leap in capability. Its extraordinary sensitivity and spectral resolution will allow it to perform a kind of remote magnetic cartography. Instead of just seeing a magnetar's average glow, Athena could potentially resolve subtle temperature variations and chemical fingerprints across its tiny surface, revealing where the magnetic field is strongest, where it is heating the crust, and how energy propagates after a starquake. It will watch outbursts unfold not as a simple flash, but as a detailed forensic timeline, tracing how energy moves from the fractured crust into the magnetosphere and out into space. Complementing this, NASA Imaging X-ray Polarimetry Explorer, or IXPE, is already pioneering a new way of seeing. By measuring the polarization of X-rays, it discerns the specific direction their electric fields are vibrating. For a magnetar, this is like finding a compass in a storm. The polarization angle carries the direct imprint of the magnetic field geometry at the source of the emission. IXPE data can tell scientists whether the field near the surface is a simple dipole, like a bar magnet, or a tangled, multipolar wreck, the result of eons of twisting and shearing. This moves us from guessing about the field's shape to directly measuring its architecture. On Earth, the next revolution will be radio quiet. The Square Kilometre Array, a colossal network of radio antennas being built across South Africa and Australia, will listen to the universe with unmatched sensitivity. Its primary quest in this arena will be to catch more magnetars in the act of producing fast radio burst-like signals, building a statistical library of these events. By capturing thousands of these fleeting bursts, astronomers hope to decode their precise origin within the magnetar's violent environment, determining if they come from near the surface, deep in the magnetosphere, or from shocks plowing into surrounding debris. Together, these instruments represent a coordinated assault on the remaining mysteries. They will allow us to move from simply knowing magnetars exist to understanding precisely how they work. We will test our supercomputer simulations against real, high-fidelity data, filling the blanks in our models of magnetic decay, crustal physics, and quantum vacuum effects. The story of these dead stars is far from over. We are just turning the page to a chapter written in higher definition, one that promises to reveal the final, twisted contours of spacetime around the most magnetic graves in the galaxy. The true nature of a magnetar is so extreme that it often blurs the line between established science and science fiction. With forces capable of twisting the quantum vacuum, it is natural for the imagination to race ahead, painting these objects as apocalyptic engines or gateways to the unknown. Yet the most profound truths about them require no embellishment. Their reality, firmly grounded in observation and theory, is astonishing enough. so let us separate the compelling science from the captivating speculation. First, while a Magnetar's outburst is titanic, its direct sphere of lethal influence is cosmically small. The dangerous range of its gamma-ray flares is measured in light-years, not the tens of thousands of light-years that typically separate these objects from us. A Magnetar is not a galactic-scale sterilizer poised to wipe out life. It is a brilliant, localized phenomenon, like a lightning strike in a vast meadow, powerful at its source but diminishing quickly with distance. Similarly, they are not celestial wrecking balls that tear apart solar systems from afar. Their gravitational pull at a distance is no greater than that of a typical neutron star of the same mass. The true danger to any hypothetical nearby planet would be the relentless radiation, not being gravitationally shredded. The intense warping of spacetime around a Magnetar is also a source of fascination, sometimes leading to ideas of them being natural portals or bridges. The science here is precise. They do curve local spacetime significantly, an effect predicted by Einstein and measurable in principle, but this is a natural consequence of immense energy density, not a rupture in the cosmos. They are extreme demonstrations of known physics, not doorways to other dimensions. This distinction is crucial. It keeps our inquiry within the realm of testable theory and observable evidence, where the real mysteries lie. Another common area of speculation involves attributing every unexplained high-energy event in the cosmos to Magnetars. While the connection to some fast radio bursts is a landmark discovery, it is not a universal key. These stellar corpses are not the solitary source of all cosmic enigmas. They are one powerful actor in a universe filled with diverse and violent phenomena, from merging black holes to supernova shockwaves. Claiming otherwise would obscure the rich, complex tapestry of the high-energy universe we are still working to unravel. By firmly adhering to the rigorously observed facts, the recorded starquakes, the measured spin-down rates, the light curves of giant flares, we achieve something far more valuable than myth. We gain a genuine, deeper appreciation for the natural marvel. The science itself reveals a narrative of staggering forces, matter in impossible states, and fundamental laws stretched to their limit. This grounded understanding allows us to ask better questions and design sharper experiments, using these cosmic laboratories not as springboards for fantasy, but as lenses to focus on the deepest workings of reality. The truth of a Magnetar, in all its calibrated, observed, and theorized glory, is more than enough to inspire awe for the genuine, untamed physics that governs the graves of stars. The abstract power of a Magnetar finds its echo in the human heart. While telescopes and equations define their physics, our species has a parallel way of understanding through story and image. These stellar corpses have become icons in science fiction, not as precise scientific models, but as embodiments of ultimate cosmic power. In novels and video games, they are often reimagined as celestial hazards, their lethal radiation fields forming impassable barriers in galactic maps, or as ancient, dormant power sources that advanced civilizations might one day attempt to harness with predictably catastrophic results. This fictional treatment is a form of translation, taking the raw, terrifying data from astrophysics journals and converting it into narrative stakes we can feel. It makes the inconceivable scale of a Magnetar's energy relatable by framing it as a challenge to be navigated or a mystery to be solved, embedding the science within a human drama of exploration and survival. Visual artists face a different but equally profound challenge: how to give form to an invisible force so strong it bends reality. Their interpretations are breathtaking exercises in informed imagination. You will see renderings where the neutron star itself is a dark, brooding sphere, but around it, space itself seems to writhe and glow. Luminous bands of color, representing those impossible magnetic field lines, arc and twist in intricate, beautiful patterns, creating a cage of light around the stellar corpse. These are not literal depictions, but emotional ones. They capture the essence of the science, the idea of space being actively shaped and dominated, and deliver it directly to our senses as sublime beauty intertwined with terror. This artistic impulse is far from trivial. It serves a vital role in the ecosystem of discovery. A compelling painting or a gripping sci-fi tale can ignite a spark of curiosity in someone who might never open an astrophysics textbook. It translates columns of data and complex theory into a visceral, immediate experience of wonder. That wonder is the seed from which public support for science grows, and sometimes from which future scientists are born. This cultural reflection reveals something fundamental about our quest to understand objects like magnetars. The drive is not purely technical. It is a deeply human response to the dramatic landscapes of the cosmos. We are drawn to these extremes, to the edges of what is possible, because they test the limits of our comprehension and force us to expand it. When an artist paints the magnetic glow of a dead star, or a writer crafts a story about a ship navigating its deadly field, they are participating in the same great project as the astronomer analyzing its X-ray pulses. They are all trying to find a place for this astonishing reality within the human experience, to make the universe feel knowable even in its most violent and alien forms. This shared endeavor, spanning disciplines, reminds us that the cold equations of physics describe a universe that is also, and ultimately, a source of profound inspiration. Our charts of magnetic field strength and our myths of cosmic power are two different languages telling the same story, a story of looking into the abyss of a stellar grave and seeing not just an end, but a magnificent and terrifying new chapter in the story of physical law. The sheer power of these objects naturally leads to a deeper question about our own motives. Why do we dedicate such immense resources to studying cosmic cataclysms, events of pure destruction on a scale we can scarcely comprehend? The ethics of this pursuit are not about the phenomena themselves, which are indifferent natural processes, but about the application of the knowledge we gain. At its core, understanding a magnetar is an act of pure inquiry, a fundamental drive to map the boundaries of physical law. This knowledge of matter under extreme pressure, of magnetic fields so strong they interact with the vacuum, forms the very bedrock of physics. It is a foundation upon which future generations may build technologies we cannot yet envision, not by harnessing the magnetar itself, but by understanding the principles that govern it. The insights ripple outward, influencing materials science, energy research, and our conception of reality itself. This research also connects us directly to our own origins. The violent supernova death that creates a magnetar is not an end, it is a vital phase in the cosmic cycle of matter. These explosions are the universe's primary forges for elements heavier than iron. The gold in a wedding ring, the uranium that powers some energy sources, the iodine essential for life, all were forged in the hearts of massive stars and scattered across the galaxy by their catastrophic deaths. By studying the remnants, we are reading the history of our own material substance, learning how the very atoms that make up our planet and our bodies came to be. This transforms the narrative from one of distant destruction to one of intimate creation, linking our existence to the most energetic events in the cosmos. Furthermore, this work quietly informs our very long-term perspective on life on Earth. The universe is an active place, and our solar system moves through it. By cataloging and understanding the spectrum of possible astrophysical events, from magnetar flares to nearby supernova and gamma-ray bursts, we improve our assessment of the broader environment. This is not about fostering fear, but about cultivating a realistic, evidence-based understanding of our cosmic neighborhood over geological timescales spanning millions of years. It is a form of cosmic awareness, allowing us to appreciate both the stability of our current epoch and the dynamic forces that have shaped and will continue to shape the galaxy we call home. Ultimately, the ethical compass points toward enlightenment. The goal is not to wield such power, but to comprehend the universe's deepest workings. Each pulse of X-ray light we capture from a distant stellar corpse is a piece of a grand puzzle, contributing to a shared human understanding that transcends borders. It is a pursuit driven by curiosity for its own sake, for the profound benefit of expanding what it means to be a conscious species in a vast and often violent cosmos, seeking to understand our place within it all. The frontier of Magnetar science is not guarded by gates accessible only to professional astronomers. This profound exploration of the universe is a shared human endeavor, and there are direct, meaningful ways for anyone with curiosity and an internet connection to contribute. Platforms like Zooniverse host citizen science projects where volunteers from around the world can help analyze real astronomical data. You might be asked to scan through light curves, the graphs of brightness over time captured by space telescopes, looking for the telltale spikes and dips that signal a starquake or an outburst from a Magnetar candidate. Your eyes and pattern recognition can help algorithms learn and identify events that might otherwise be missed in the vast flood of data, turning your screen into a portal for cosmic discovery. For those with a more hands-on approach, amateur astronomy offers another path. A dedicated amateur with a backyard radio telescope can monitor the steady pulses from known neutron stars, including magnetars when they are in a quiet phase. By meticulously tracking the arrival times of these pulses, a global network of enthusiasts can help professional scientists detect the subtle glitches and timing anomalies that signal internal changes within these distant corpses. This collaborative monitoring creates a continuous watch on the sky, providing valuable long-term data that large observatories, with their limited observing schedules, cannot always gather. Staying informed is itself a powerful form of participation. By following the social media accounts and press releases of organizations like NASA, the European Space Agency, and major observatories, you can become a first-hand witness to discovery. You might receive an alert that a magnetar in our galactic neighborhood has just erupted, and within minutes, you can look at the initial data or an artist's interpretation, sharing in the moment of revelation. This immediate connection transforms abstract science into a living, breathing narrative happening in real time across the cosmos. Engaging in this way does more than feed personal curiosity. It strengthens the entire ecosystem of exploration. Public interest and demonstrated engagement are vital factors that help agencies justify the ambitious and often expensive missions needed to push our understanding further. When you classify a light curve, report an observation, or simply share news of a magnetar's outburst with wonder, you are voting for a future of discovery. You help cultivate a culture that values looking up and seeking answers, ensuring that the next generation of telescopes and the scientists who use them have the support to keep listening to the magnetic whispers of dead stars. There is a quiet poetry in the fact that a magnetar's power is born from its ending. We are observing a stellar afterlife, a phase of existence defined not by the fusion that once gave it life, but by the indelible imprint left behind. That unimaginable magnetic field is the star's final signature, written in the language of twisted spacetime and quantum fire. It is a form of cosmic memory, a persistent echo of the cataclysm that forged it, carrying the story of a rapid spin and a violent collapse across millennia. This transforms our perspective on cosmic death. For a star, the supernova is not a full stop but a semicolon. The narrative continues in the graveyard, where the remnant becomes something entirely new, often more extreme and influential than its progenitor ever was. The quiet, stable sun that nurtured life on Earth will one day fade into a cold, dense ember. but a massive star, through its spectacular demise, can become a magnetar, a lighthouse of force that continues to interact with and even illuminate the galaxy for ages. This shift from a source of light and heat to a source of pure magnetic power is a profound metamorphosis. It suggests that in the universe, an ending is rarely an erasure. It is more often a transmutation, where the energy and structure of a life are converted into a different, lasting form. The star's mass becomes incredible density, its spin becomes a magnetic dynamo, its death throes become an engine for future cosmic events. Nothing is truly lost, it is all relentlessly recycled and reshaped by physical law. This cosmic process holds a mirror to our own human contemplations on legacy. We, too, think about what endures after a life concludes, about the energy we impart to the world that continues to resonate in our absence. A magnetar makes this abstract concept viscerally real. It shows us that an ending can concentrate and amplify certain qualities, creating a lasting force that actively shapes the environment for eons. The star does not live on in a biological sense, but a fundamental part of its identity, its magnetic character, achieves a kind of immortality, influencing the flow of particles, the propagation of light, and the very fabric of space around it. It becomes a permanent part of the galactic landscape, a monument not of stone but of structured force. Observing these stellar ghosts, we are reminded that our definitions of life and death, of activity and passivity, are wonderfully provincial. The cosmos operates on a timescale and with a creativity that constantly challenges our categories. In the silent, magnetic vigil of a dead star, we find a powerful allegory for transformation, reminding us that even in endings, the universe is brimming with potential for new and astonishing forms of existence. The stellar graveyard holds more than one kind of ghost. To fully appreciate the magnetic fury of a magnetar, we can place it beside its more famous cosmic cousin, the black hole. Both are born in the same catastrophic furnace, the collapse of a massive star's core during a supernova, yet their afterlives could not be more different, representing two ultimate extremes of physical law. A black hole is the embodiment of gravity's total victory. When the collapsing core is too massive to be stopped by any known force, it crosses a point of no return. The curvature of spacetime becomes infinite at a central singularity, and an event horizon forms, a boundary from which not even light can escape. The black hole is defined by concealment, by the ultimate privacy of its interior. We can only infer its presence by its gravitational influence on nearby matter and light. A magnetar, however, tells a story of a stalemate. Here, the inward crush of gravity is perfectly balanced, at least temporarily, by the outward pressure of degenerate neutrons, a quantum mechanical force that says matter cannot be compressed further. But the magnetar adds a third, dominant character to this balance, its own magnetic field. This immense force doesn't just exist within the star, it actively supports and stabilizes the structure, twisting the very fabric of the star's solid crust. So while a black hole is defined by what it hides, a magnetar is defined by what it violently, brilliantly reveals. Its entire identity is broadcast through its magnetic outbursts, its X-ray glow, its seismic starquakes. This extends to how they warp the cosmos. A black hole curves spacetime with its mass alone. A magnetar achieves a similar, though lesser, curvature through the sheer energy density of its magnetic field. It is a profound demonstration that in Einstein's universe, energy and mass are two sides of the same coin, both capable of bending the stage of reality. This comparison illuminates the diverse portfolios of power within dead stars. One ghost rules through pure, silent gravity, a shadow that consumes. The other reigns through ferocious, luminous magnetism, a beacon that screams across the galaxy. Both are permanent, sculpting their corners of the cosmos long after the star's light has gone out, reminding us that death for a star is not an end, but a transformation into new and lasting forms of influence. Even with our advanced models and telescopes, these stellar corpses guard their deepest secrets closely. The precise recipe for a magnetar's birth remains one of the most tantalizing puzzles. We know the general ingredients: a rapidly spinning, massive star collapsing in a specific way, but the exact sequence of events in those final milliseconds is still a theoretical frontier. Does the magnetic dynamo ignite in a single, coherent process, or is it a chaotic cascade of smaller events? Different simulations produce different answers, and without being able to witness a supernova up close, we must rely on the subtle signatures imprinted on the remnant itself. This uncertainty extends to the star's entire life cycle. The slow, steady fade of a magnetar's X-ray glow tells us its magnetic field is decaying. But how? Is the energy slowly leaking out as heat from the crust, or is it being consumed in the turbulent superfluid core where magnetic filaments slowly dissolve? The rate of this decay is our only window into the star's exotic interior composition, yet we still lack a definitive map of that hidden realm. This leads to another fundamental question about identity. Are all magnetars born in that initial, perfect storm of collapse and dynamo action, or can a relatively ordinary neutron star become magnetized later in its life? Some theories suggest that if a neutron star accretes or pulls in matter from a companion star in a binary system, the infalling material could spin it up and reignite a dynamo, effectively creating a magnetar through a second act of cosmic violence. If such objects exist, they would blur the line between different classes of stellar corpses and suggest that magnetic fury is not solely the privilege of a solitary, explosive birth. Finding one would revolutionize our understanding of how these objects populate the galaxy. Then there is the connection to fast radio bursts, a link that is firm but not yet fully understood. Is every giant flare from a magnetar capable of producing an observable radio burst, or does it require a very specific set of conditions, like a particular configuration of surrounding debris? Furthermore, could magnetars be responsible for all types of fast radio bursts, including the incredibly energetic non-repeating ones from distant galaxies, or are they just one contributor to a cosmic chorus of mysterious signals? Each new localized burst, especially from within our own galaxy, provides critical data, but a complete theory that explains every single detection still eludes us. Pushing the boundaries of possibility even further, theorists wonder about objects even more extreme than the standard magnetar. Could there be quark magnetars where the core pressure is so immense that neutrons break apart into a soup of free quarks, creating a fundamentally different kind of magnetic engine? Or what about hybrid stars with layers of different exotic states of matter, each influencing the magnetic field in unique ways? These ideas are not pure speculation. They are natural extensions of our physics, but they exist just beyond the edge of current observational proof. Detecting one would be a landmark discovery, revealing a new state of matter in the universe. These open questions are not dead ends, they are the very engines of discovery. Each mystery drives the development of more sophisticated computer models and demands the construction of more sensitive telescopes. They ensure that the study of these magnetic ghosts will remain a vibrant, dynamic field for decades to come, as every new flash of X-rays or flicker in a radio signal brings us one step closer to unraveling the final, twisted truths written in spacetime around a dead star's grave. This entire journey reveals a single, continuous epic written in magnetic fire. From its first moment, a magnetar is a story of transformation. It begins not with a quiet death, but a spectacular rebirth within the supernova's fury, where a star's rapid spin and violent collapse forge a magnetic prison of unimaginable strength. This field becomes the star's new identity, a defining force that actively shapes its afterlife. It torments the solid crust, building stress until it fractures in starquakes that release more energy than our Sun emits in millennia. Occasionally, that stress triggers a catastrophic reorganization, a giant flare that can briefly outshine entire galaxies. The influence extends beyond mere outbursts. That concentrated magnetic energy warps the local fabric of spacetime, contributing to gravity's grip, and twists the quantum vacuum, making empty space itself behave like a strange crystal to light. This is not a static monument but an evolving entity. Over thousands of years, the magnetic field slowly decays, its energy leaking out as heat that keeps the star's surface glowing fiercely in X-rays, a steady beacon powered by internal magnetic friction. This gradual fade is the final chapter of its active phase as it transitions into a more typical, quiet neutron star, its legendary fury spent. Yet, throughout its brilliant and violent lifetime, the Magnetar performs an invaluable service. It acts as the universe's most extreme natural laboratory. Every quake, every flicker of its X-ray glow, every subtle change in its spin provides a direct test of physics under conditions we can never replicate. It probes the limits of general relativity and quantum electrodynamics, and its most violent moments may be the source of mysterious cosmic signals like fast radio bursts, linking this stellar corpse to mysteries across the cosmos. The true legacy of a Magnetar, therefore, is dual in nature. It is a testament to transformative power, showing how a star's end can birth an object of even greater, though different, influence. And it is a profound scientific gift, a cosmic beacon that willingly broadcasts the secrets of fundamental law from its grave, offering us a front-row seat to the most extreme physics in the universe. The story of Magnetars is ultimately a story about the universe's capacity for wonder. Our exploration of these dead stars reveals a cosmos far stranger and more dynamic than the quiet, static sky often suggests. These are not mere cosmic oddities relegated to a specialist journal. They are extreme natural experiments operating on a galactic scale. Each flicker of their X-ray light, each sudden starquake, challenges the very foundations of our understanding, stretching the laws of physics from the bizarre rules of the quantum vacuum to the grand curvature of spacetime itself. In their violent lives and slow magnetic deaths, they narrate chapters of stellar evolution we could never witness directly, teaching us about the transformative power of cosmic cataclysms and the enduring, invisible architecture of magnetic force that can outlive a star by eons. Every new observation from a space telescope, every breakthrough in a supercomputer simulation, brings us incrementally closer to answering questions that sit at the heart of reality. The true nature of matter under pressure, the relationship between energy and gravity, and the final fate of the most powerful fields in existence. So the next time your gaze lifts to the night sky, remember that hidden among the familiar points of light are these magnetic monsters, their silent, invisible might perpetually bending the fabric of the cosmos around them. If this journey to the farthest edges of physics captivated you, consider subscribing for more deep dives into the universe's greatest mysteries. We would love to hear your thoughts on these incredible stellar ghosts in the comments below.